Welcome to the next video in measure theory and probability. This is video 8 on operations on measurable functions. This corresponds to part 1, chapter 1, section 3 of the textbook. So we're going to start with a sort of common domain, right? This EA is going to be a measurable space that is going to be the domain of several functions we're about to introduce. We'll take some two measurable spaces and equip them with the product sigma field. Now, suppose that f1 is a function from e to f1. f2 is a function from e to f2. So we have two functions, and we form a third function f from e to the Cartesian product f1 product f2 in kind of the natural way where f1 and f2 just make up the components of this new function. The claim here is that f is measurable if and only if each of the components is measurable. Let's prove this in the left to right direction first. So we're going to assume that f is measurable, and now we're going to prove that f1 is also measurable. To prove that f1 is measurable, we need to select some measurable set from its range and show that its pre-image is also measurable. So effectively, this is what we want to show. Now, how are we going to do that? We need somewhat clearly to leverage the measurability of f. So we can't just work with this set B. Rather, we have to somehow construct a set which can be given to the to kind of like the pre-image map for f. So what set should we construct for the input here? Why should it be this set? Well, we certainly need to get a measurable set, right? And so f2 is certainly measurable in the second sigma field because this is part of, right, it's the entire set, and one of the properties of sigma fields is that they always contain the entire space. So it's measurable, and therefore, when we form the Cartesian product, that is measurable in the product sigma field. So great, so we have a measurable set, but why still, right, how do we justify this equation between the two so that we are still talking about the pre-image of B for F1? Well, it may be clear if I just kind of give some steps from a formal proof, really. So let's talk about the proof that, So let's start with the proof of this set equation, right? After all, this is a set, this is a set. We'll talk about how we would prove that they are equal to each other. And so I'm going to take an element out of this set and prove to you that it is in this set. Now, how are we going to give that proof? Okay, so we take this element, and immediately by definition, it just means that f of x is in B. Sorry, f1 of x is in B. Now, to prove that x is in this set, then I need to consider f of x. So let's talk about f of x, and that is equal to, by definition, f1 of x, f2 of x. And notice that we just said that this component is in B, and this component, well, it certainly is in F2, which is exactly what we need to be talking about. We need to be talking about this thing landing in B cross F2. And so we need, right, like, this is why the choice of F2 was the right choice, is that effectively, to get exactly this membership that we need for the proof, we kind of want to free pass on this second coordinate, right? I want to make sure that no matter what this is, it is an right? It lands in an acceptable place, right? Well, if that set there is f2, then anything in this coordinate is acceptable. And that's really the reason why f2 was the right choice for this particular step. So, right, just to complete the thought here, we get that x is in the pre-image of B cross F2. The other direction is even easier, so let's just do it real quick. Let x in the pre-image of B cross F2. And this just means right, so we get that the image of x is this coordinate f1x comma f2x, and because it is the pre-image of B cross f2, that means that this image must be in B cross f2. Okay, well, certainly by definition of being there, we can focus on only the part we care about, which is that f1 of x is in B, so that's what we get here. And then this immediately, by definition, tells us that x is in the pre-image of B for f1. So anyway, there you go, proof complete. But really, it's this step here that was the reason, right? It's the explanation for why we wanted to set f2 here. Anyway, having done that, now that we have the equation, this basically shows us that that this set is in A, because after all, right, f is a measurable set, and we're taking the pre-image of a measurable set, so you must get something measurable, right? It must be in A. So there you have it. That's the proof. This shows that f1 is measurable, and the proof that f2 is measurable is very similar. Next, let's move on to the right to left direction. So we're going to assume that f1 and f2 are each individually measurable. We need to show that f is measurable. We will use a technique that I think we've seen a couple times now, which is that we will take a generating set, right? So rather than pick an arbitrary element out of the product sigma field, rather we'll take something out of a set that generates it. And in particular, it's somewhat obvious based on the definition of the product sigma field that the right collection to pick which generates it is by definition, right? This collection, the collection of all Cartesian products, is by definition the collection that generates the sigma field, the product sigma field. And so certainly that's like the most obvious choice for generating set here. I think I wrote something not accurate here, so let's just ignore that. But in any case, right, so we know what the collection is. We're going to pick an element D out of that collection. D necessarily is some D1 cross D2, where D1 is an element of B1, D2 is an element of B2. So here's an arbitrary selection from that generating collection. By definition of being in B1, we get that the pre-image of D1 is measurable, which is to say an element of A. The pre-image of D2 is measurable also for the function f2, again, all by definition. And so if each of these is measurable, somehow we need to relate this to the pre-image of D1 cross D2. Well, with a bit of set theory, right, basic set theory, you should be able to prove that the pre-image of the product is the intersection of the two pre-images. Now, we have that each one of these is measurable, and we have that any sigma field is closed under intersections, and so therefore their intersection is measurable, and that completes the proof. Okay, let's now look at another theorem. So we're going to take some two functions that share a common domain E, which is going to have some associated sigma field which we'll call A if we have to talk about it, but we may not. In any case, it will take values in the real numbers and we'll assume it to be measurable. Keep in mind, whenever we talk about a function being measurable and its range is the real numbers, then we're talking about the sigma field, the Borel sigma field, right? That's the sigma field put on the range. Okay, the claim is that the sum of f and g, the product of f and g, these are measurable. Also, if you took the inf of f and g, and here what we mean when we say that is we're taking this pointwise. So if you think of inf fg, how does this map some particular point x? Well, it is just the inf between the 2 points f of x and g of x. In fact, this is nothing other than the minimum, because when you have a finite collection of things, then the infimum is the same thing as the minimum. But so that is the inf of f and g. Likewise, we have the sup, which is effectively the same thing as the max. All of these are taken pointwise, which basically means that this is how you compute these values. Then we have this thing which is the positive part of f. Now, don't confuse this with the absolute value. I think that would be a common confusion. The positive part of f, if you want, this may help you to visualize it. So take some f that has positive and negative values. The positive part of f is the part that is positive. When it goes negative, it simply flatlines along 0, right? So we are taking the sup between f and 0. So, here f is bigger than 0, so we're selecting this portion of f. But here f is less than 0, so we simply select 0 until it becomes positive again when we select the positive values, right? So that is the positive part of f, right? Where it is positive, you select the positive values. Where it is negative, you select 0. And then we also have the negative part of f, and this, keep in mind, is going to be made up of positive values. So if you think about taking the negative of f, right, that would be, you would effectively flip the graph of this function to get negative f. Here's a rough drawing. And then we're going to select its, basically the sup between it and 0, so that we now get this thing right here, and everywhere else we get 0. So that's 0. So this orange curve is the negative part of f, right? So f, recall, is just that original black curve, and the positive part of it is drawn in pink, and the negative part of it is drawn in orange. And notice that, right, the positive part and the negative part are both positive quantities. So keep in mind, right, if you want sort of a nice relationship back to f is just equal to, actually I'll just write it like this, f is equal to the positive part minus the negative part. So anyway, the claim is that with all of these functions so defined, every single one of them is measurable. To demonstrate this, we will use the above theorem about, right, product spaces and functions and so on, together with composition. So effectively what we're going to do is take a single point and, right, especially for the addition part, well, really for all of it, and so we're basically going to take a single value and map it over to its product space for f and g. And then we will take that point and apply whatever given function we want, right? In this particular case, addition. Now, here we're going to take it for granted that addition is a continuous function, and therefore it is a measurable function. And that effectively gets us two measurable functions, right? This function we know to be measurable from the previous theorem because we know that f and g each individually are measurable, because again, that was the assumption in the theorem. So we have that the first function is measurable, the second function is measurable, their composition is therefore measurable. Proof complete. Oh, and the other functions I'm kind of leaving as an exercise, right? We'll take it for granted that multiplication is continuous, or if you want, right, you can prove that any one of these functions is continuous. And of course, if anybody is actually interested, I can come back when, right, like leave a comment requesting a proof to show that these things are continuous, and I can do that. But if I don't have any indication that there's interest in that, then I'll just skip it. Okay, here's another function, somewhat similar. Suppose that we have a sequence of functions and they are each measurable. They have shared domain E and they take values in the extended real numbers. I believe in previous videos I wrote the extended real numbers with the notation that is familiar to me, this R star, but it looks as though the book just uses R bar for the extended real numbers, so I'm going to try to switch to match the notation of the textbook. The claim then is that these functions are all measurable, and of course they are also defined pointwise like in the previous theorem. So, right, so for instance, sup n So how does this function sup n fn, how does it map a single point? Well, you simply take that point, map it according to all of the fn's, and then over that set, you take its supremum. So that is a pointwise definition of this function. And likewise, you pointwise define each of the other functions. Moreover, as a quick consequence of this, if a function converges, right, if the sequence of functions converges pointwise everywhere, then the limit is also a measurable function. That is to say, right, let me just write it real quick, that lim n to infinity fn is measurable, where again we're assuming that this sequence converges pointwise everywhere in E. Okay, for the proof, we'll again use a generating set, this time for, and I think we need to take not the Borel sets on the real numbers, but the Borel sets on the extended real numbers. Yeah, but we only need these intervals to get the Borel sets on the extended real numbers. I'll leave that as an exercise, or again, you can request a proof if you need it. So let's just pick the sup. I think the book showed it for the inf, so maybe just for a slight variety, I'll show how to do it for the sup. It's almost exactly how the book does it for the inf. So we need to show that the pre-image on any one of these generating, right, elements of the generating set, we need to show that its pre-image is measurable, right? So here, right, picking one of these members of the generating set is essentially the same thing as picking any real number and then looking at the pre-image of that interval. Now let's, of course, talk about that pre-image. That's where we need to get started for this proof. And, think about the fact that the pre-image of this soup function is the set of all points in the domain such that if you take the soup over all of your functions, you get a value which is strictly greater than a. Now, somehow we need to show that this thing is a measurable set. And if we think about the nature of this set, well, if a single value of fn of x, right, like pick a particular x, and if at that particular x, any one of the fn's is less than or equal to a, then the soup over all of them will be less than or equal to a and not a point that we want. But now notice something about this sequence, right, or this set. Pick some particular point, and it may help to draw a diagram. So let's imagine that you've got some function f1, and maybe it's getting bigger and bigger, and we're really only interested in one particular point, right? So let's maybe say that like the point that we're interested in here is this. Maybe we're talking about whether the soup is greater than a. Now, if this thing keeps like increasing and increasing, we could even get it up, like as these functions get closer and closer, if it converges to a, or even if it runs through a at some point, then we would have that the soup is less than or equal to a. And similarly, if the values all stay strictly below a. So the only way for the soup to be strictly greater than a is you have to have some function that actually pops up above the value a, right? So effectively, what I'm getting at here is that a particular point x is in this set if and only if some particular function maps x above a, strictly bigger than a, right? So that's the kind of quick argument, somewhat pictorial, that we need some point above a for some one of these functions. Now, that gives a strong hint to a good move to make. If we need some point above a, well, whenever you're talking about there being some such element, you're kind of, implicitly talking about a union. Because after all, right, what is a union of sets? It's the collection of all points that are in some one of the various things you are unioning. So effectively what I'm arguing is that this set in question is a union over all of the points for each individual n, right? So if you fix an n, this set is only for the nth function, right? And so here we're saying that there exists some function for which the point x is mapped above a, right, by that particular function. So anyway, the important thing here is that we have turned this into a countable union, right? And each one of these sets, by the way, is measurable, right? That's also important to emphasize, is that for a particular fixed n, we're just talking about the pre-image of this interval for the nth function. Well, because each individual function is assumed to be measurable, and we're taking the pre-image of some measurable set, then this must be measurable. So what we now are seeing here is that we are talking about a countable union of measurable sets, and therefore because a sigma field is closed under countable unions, then therefore this union is measurable, okay? Countable union of measurable sets is measurable. So we now have that this set that we were interested in, effectively this set right here, this set is a measurable set from this proof. Therefore, the function f is a measurable function, and that concludes the proof. The proof that the infimum is measurable is given in the book, but it's also just a slight change from the proof given here. And then let's talk about the lim sup. How do we know that the lim sup is measurable? Well, here we probably want to use this convenient little result that the lim sup is actually the same thing as, if you take the sequence of sups, its infimum, right? The infimum over the sequence of sups is actually the same thing as the lim sup. And this has to do with the fact that, this is not completely unique to lim sup. If you have any monotonically decreasing sequence and you take its limit, that limit is always equal to the infimum of the sequence. It's a worthwhile fact from real analysis to recall. But anyway, so that applied in this particular case gets us that the lim sup, because the sups are a monotonically decreasing sequence, and so if you take its limit, then it's actually the same thing as taking the infimum. So anyway, the point is that the lim sup is the inf of the sups of the functions. And because of that, right, so we have effectively that this is a measurable, right, like because each one of these is measurable, and we proved that the sup over measurable sets is measurable, then this sup thing is measurable, and then because we also know that the inf over measurable sets is measurable, then therefore taking the inf keeps it measurable, and now we have that this thing is measurable. Also, let's just comment on that last little piece of everything, which said that if the limit exists, then it is measurable, and that is just because if the limit exists, well, then it is the same thing as the lim inf. Of course, I could have also said it's the same thing as the lim sup, but right, when the limit exists, it's equal to both the lim inf and the lim sup. So anyway, let's just talk about the lim inf. Since the limit exists, it is equal to the lim inf, and we already showed that the lim inf is measurable, so the lim is measurable. There, that concludes the proof.